A lot of times in physics and chemistry, some type of scientific phenomena may be described verbally, given some kind of, some kind of existing rule or existing physical law that allows you to relate two or more variables together, and they can be translated into mathematical statements. More often than not, the words proportion or direct variation may be used in that description. For example, this statement that says x varies directly with y, or it could also say x is directly proportional to y, means that x equals some constant times y. The constant k is used to denote what's called a proportion constant. So keep in mind, if x and y are directly proportional, that just means as y gets bigger, x gets bigger. As y gets smaller, x gets smaller. It does not mean that x and y are equal to each other. It just means that they grow proportionally with each other. So anytime you have two variables that are related by direct proportion or varies directly, you're going to have one variable equals k times the other, like this. It's required to have that constant there because you don't exactly know what the value of the constant is until you get some data about the variables x and y. So an example is if you're asked to take this sentence and translate it into an equation, the variable m varies directly with the cube root of r. Now keep in mind, this does not mean that m equals the cube root of r, it means it varies directly with. So those words right there guarantee that this is true. M equals some constant k times the cube root of r. So you'll just pull up a cube root symbol and put r inside the cube root, and that's exactly the mathematical sentence that you need to get from that verbiage. Okay, so anytime two quantities vary directly or are directly proportional, that's the way the equation should be translated. Okay, now in an application of this, we've got an example of something that uses direct proportion. For an object that's subject to free fall, the distance that it falls, d, varies directly to the square of the number of seconds, t, since it was dropped. So there are two variables mentioned so far. The distance that the object falls, d, is directly proportional to or varies directly to the square of the number of seconds, t, since it was dropped. So be careful about any other modifiers like the cube root mentioned here or squaring that's mentioned here. D varies directly with the square of t, means d equals k times t squared, or d equals kt squared, where k is that proportion constant we don't know just yet. But in this problem, we are given some data that relates d and t together. So for this object in free fall, it takes 3 seconds for an object to fall the distance of 144 feet. Then you're asked to figure out how far will the object fall after 6 seconds. Okay, so this is where you're going to take the first sentence that gives you the data, 3 seconds of time, so that's a t value, that's going to use t equals 3, for an object to fall the distance of 144 feet. So the falling distance is 144. So based on that first sentence, we can take for granted that at a value of t equals 3, the distance d is 144. So plug in the values that you know, and then solve this for the value k. You've got 144 equals 9 times k. So then when you divide both sides by 9, that's going to give you k equals 16. So what that means is, after having that first little bit of data translated into the equation, we can now take the original statement and replace k with what it actually stands for. For this particular situation, d equals 16 times t squared. So once you know the value of k, you can relate d and t together for any other measurements that you might need. The last thing you're asked to find is, how far will the object fall after 6 seconds? Well, 3 seconds gives you 144 feet of falling distance, so 6 seconds is going to make it a little bit further. So d equals 16 times 6 squared. So if you crunch that out carefully, you've got to do 16 times 36, and that's going to give you 576. So at 6 seconds of travel time or falling time, that object's going to fall 576 feet. So the ultimate answer would be 576 feet, based on the fact that distance and the square of time are related directly like that. So that's one particular type of variation. This first page just exemplifies direct variation, x equals k times y. Now, and again, the unique thing here is as one quantity increases, the other quantity increases. So you've also got the inverse relationship. As one quantity increases, the other quantity may decrease. That's an example of inverse variation. So if x varies inversely with y, or x is inversely proportional to y, then the equation that generates is going to be x equals our proportion constant k divided by y in this case. So anything that follows the words inversely, if you see that adverb used in the description, anything that's inversely proportional or varies inversely is going to divide underneath the k constant. So values which vary inversely, an increase in one causes a decrease in the other. So here's a simple sentence that we need to translate into an equation. F varies inversely with the fifth power of p. So since we see varies inversely in there, that means F equals k divided by, and that's what tells you to put that there, is varies inversely, divided by the fifth power of p. So divide by p raised to the fifth. And that's exactly the mathematical statement that sentence is generating. F varies inversely with the fifth power of p. Okay? So another example that deals with inverse variation between a couple of quantities. In kickboxing, the force F that's needed to break a board varies inversely with the length L of the board itself. So just the first sentence alone tells you the relationship you need between F and L. The force F varies inversely with, so equals k divided by, the length of the board. So you just divide by L. There's no squaring or fifth powers or cube roots mentioned, so F equals k divided by L is the simple equation that generates. Now, if it takes 5 pounds of pressure to break a 2-foot long board, so in other words, 5 pounds is going to be your force amount, and that's technically ill-worded. That actually should say force. Pounds measures force, pressure is completely different units altogether. So that's just me nitpicking, so just disregard that. Anyway, 5 is going to be the value that you plug in for F, representing pounds of force, and then the length of the board is 2 feet long. So that second sentence right there tells you that it takes a 5-pound force to correspond to a 2-foot board. So plug in 5 for the force and 2 for the length, and this allows you to solve for K. To solve for K here, multiply both sides by 2, or cross multiply by 2, and you get the value of K is going to equal 10. And so just like in our previous example about free fall, now that you know the value of K, you can take your original equation and specify it using your value of K that you determined. So that way, if we need to use this formula again, we can take for granted that K equals 10 in this case. So F equals 10 divided by L. So then finally what's asked to figure out is how much force is needed to break a 6-foot long board. So if we know the length goes to 6 feet, force is going to equal 10 divided by 6 feet long. So 10 divided by 6, that reduces to 5/3. So the force is going to equal 5/3, and be careful of your units. Force is measured in pounds and length is measured in feet. So since we're given 6 feet for the length, this corresponds to 5/3 being F. If F equals 5/3, we have to use F's units to represent that answer. So that means it will be 5/3 pounds, or if you want to write that as a mixed number, it's okay. Usually I just leave it as an improper fraction like this, but if you want to go ahead and call that 1 2/3 pounds, either one of those are fine for the statement of how much force is going to go there. And that's, so that kind of makes sense. It took 5 pounds to break a 2-foot board. So since force and length are inversely related to each other, if the length goes up, the force needs to go down. And that kind of makes sense if you think about it. A longer board wouldn't take as much force to break if you had to kick it. So since you go from a 2-foot board to a 6-foot board, the length increases. That means the force went down from a 5-pound force to just a 1 2/3 pound force. So force decreased. And that's the essence of things that are inversely related to each other. One quantity increasing causes the other quantity to decrease. Okay? And the other kind of variation that I need to show you is what happens if you have multiple variables involved. For example, this sentence just involves 3 variables, x, y, and z. And so it said that x varies jointly with y and z, or it says x is jointly proportional to y and z. If you have 2 or more variables in that relate back to your original x over here, all that means is you just keep multiplying them together. X is jointly proportional, so x equals k times y and z, so y times z. So if you had x is jointly proportional to p, m, and q, you'd have x equals k times p, m, and q. And also be mindful of other things, like if you see the square of y or the fifth root of z, you need to make sure those go in there as well. But any of these proportion statements are only going to make products or quotients with your k. You would have to deliberately see the word sum or difference mentioned there in order to use addition or subtraction. Any other implication is that the variables are going to be multiplied or divided into your k. Okay? So no matter how many variables are used after the proportion statement, you only need one value of k for the entire equation. So you don't need a separate k to go with the y and a separate k to go with the z. One k is all you ever need to make any particular type of proportion equation. So this example states that h varies jointly with w and the square of z, and varies inversely with the cube of m. So h is related to 3 other variables in this mix. And according to what's read from left to right, it says h varies jointly with, so just the h in those next 3 words right there tell us that h equals k times, varies jointly with w, okay, so h equals k times w, varies jointly with the square of z, square, not square root, so that means h equals k times w times z squared, and varies inversely. So anytime you see that adverb inversely used, that lets you know to make a fraction bar, because whatever follows inversely is going to go in the bottom of your proportion on the right hand side. So varies inversely with the cube of m, so m raised to the 3rd power. So translating that sentence correctly, h varies jointly with w and the square of z, and inversely with the cube of m. That's the translation of this as a mathematical sentence, as an equation. And then you're given 2 sets of data, one that's complete and one that's incomplete. The first one allows you to plug in all 4 values for everything except k. So according to the first one, if I plug that in correctly, h equals 20, so h is going to go to 20, equals k times w, so w equals 6, z equals 2, so don't forget to square that, so 2 squared, and then m equals 3, so divide all this by 3 raised to the 3rd, and then this should help you find out your value of k, your proportion constant. So notice you can do some cross multiplying and cross dividing here. Cross multiply by the 3 to the 3rd. That's going to give me 20 times 3 to the 3rd equals k times 6 times, I'm going to go ahead and make that a 4. So then divide both sides by 24 to get k by itself. And so then if I crunch that out carefully on the calculator, 20 times 27 divided by 24, that's going to give me, okay, I'm going to go ahead and make it a fraction. K equals 45 halves in this case, okay? Or since halves convert easily to decimals, you could even go so far as to say 22.5 if you want to, equals your k. So that should be the value of k that you're getting based on this original data that we have up here in the equation. So with that value of k, then I can refine the original equation to say h equals 22.5 times w times z squared, all divided by m to the third. And then we can take the second bit of data that we've got, the value of w, z, and m, and plug those into this to figure out the value of h that corresponds to it. So once the data changes, w is going down, so 22.5 times 2 for w. Z is also going down, so 1 squared, and m is going up. So these two vary directly with h. Them going down means h should go down. M varies inversely with h, so since it's going up, h should also go down. So all these variable changes should guarantee a decrease in your h quantity. So dividing by m to the third is 4 to the third. So if I crunch this out carefully in the calculator, that's going to be 22.5 times 2 times 1 squared, so no need to actually type that in there. And then divided by 4 to the third is 64. I'm going to put the fraction symbol on the end of it just in case it turns into a fraction. So h equals 45/64, or if you want that as a decimal, that would be, well, exactly, since it terminates, that's 0.703125. So the original value of h was 20, and then it goes down to being less than 1. So yeah, decrease in w and z guarantees a decrease in h, and then since m is inversely proportional, an increase in m also guarantees a decrease in h. So h decreased a good bit by the time we got through the data, decreased to being less than 1. Okay, a little more than 7/10. So that summarizes everything you need to know about variation. A relatively short lesson, just one video needed for this section.